Hello and thank you for watching. This will be a three-part series on electric circuits. This part will be focusing on some of the basics with regards to electric circuits. So let's get cracking. We'll start off with electric current. Remember, electric current is the rate of flow of charge and can flow through a complete electric circuit. An electric circuit requires a few things, and they are an energy source in the form of a battery or a cell, conducting material, mostly copper wire nowadays, and of course an appliance that you want to run. Conventional current flows from positive to negative, but in actual fact it flows from negative to positive. But because of how it all started off, the belief was from positive to negative, and it's still sort of work with that concept. We still work with the concept today. So looking at the different types of circuits, there are two types of circuits. But generally speaking, there's a series circuit where we have over here just one single path for resistors to flow through, for current to flow through, and then here for parallel connection we have two paths for the current to flow through. In this example there can be multiple paths. In this example there are two paths, and this is the symbolism used for a resistor. That's the symbolism used for switch, and of course here we have a number of cells. Then with regards to these types of circuits, a series connection has resistors that are connected so that current flows only through a single path, like we just saw in that previous diagram, and the entire circuit can be controlled by a single switch. This also means that if one of the resistors had to malfunction, had to break or blow, then the entire circuit will experience no current flowing through it because the circuit is broken. And now looking at the parallel connection, resistors are connected so that the current can flow through more than one path, and the current will be divided when there's more than one path. There will be more on this topic in a video to follow. But current is divided in these paths, and if one resistor is blown out or is broken or malfunctions, the current still flows along the other paths. So if we look at this diagram here with these two light bulbs, if the one breaks or blows, then this one will still continue to work even though there's no current flowing through that one, because there's more than one path. Let's have a look at potential difference and EMF. Very similar concepts, but there are still differences. So EMF actually stands for electromotive force, and it's explaining the energy supplied by the electrons and how they deliver this energy to the rest of the circuit. So like I said, the total energy supplied per coulomb of charge. This is just an equation to work out voltage, because that's what EMF is measured in. It's measured in volts, and the W over here represents energy and the Q represents charge, so the energy per coulomb of charge. The EMF can be measured in volts, like I said, and it can be done by attaching a voltmeter across the battery terminals, and there doesn't have to be, you don't require a flow of current, so you can have an open switch. So that's pretty useful. Potential difference is similar but different, because now we have the current flowing. It's the voltage across the battery terminals while the current is flowing, so you have a closed switch. We will be discussing that in more depth in a later video. Electric current, like we mentioned earlier, it is the rate of flow of charge, and it's measured in amps coulombs per second is how we work out, or one way of calculating current. Like we said earlier as well, conventional current flows from positive to negative. And this is just a simple this is just a simple formula we can use to calculate current. Moving on, just an example of the type of question we can ask. A bulb requires 0.25 amps to shine bright. How much charge moves through the bulb in 10 minutes? So we are given current and we are given time in minutes. They're asking for charge. So let's have a look at the solution. Using this formula over here, we substitute our values in. We've got the current, we've got the time, but it's got to be converted to seconds. So you multiply the 10 minutes by 60 to get into seconds, and your answer is 150 coulombs. Pretty simple. Then you can also expand on that by asking how many electrons move through the bulb in 10 minutes. So the previous question was based on how much charge. Now it's asking how many electrons. So using this formula over here, which we also use in electrostatics, this is the charge of an electron, and this is the number of electrons. That's what we want to work out. That's the unknown. So we substitute our values in, and we get our answer. Many electrons required for a small amount of current, 0.25 amps, but bearing in mind that it is for 10 minutes. Just very quickly, how do we measure voltage and current? Voltage is measured with a voltmeter. It must be connected in parallel with the component of interest. It cannot be connected in series. It's got a high resistance. It must be connected in parallel to measure the potential difference, because that's what the measurement of voltage is. And then current has got to be by using an ammeter connected in series with the component of interest. Alright, so this is just a diagram of what it looks like. That's very clearly in parallel connection there across this bulb, and then this ammeter is in line of the path where it wants to measure the current, and it's in series, it's not in parallel. Right, so that concludes the end of the first part of the series. Please comment if you have any questions or likes, and have a look at my next video that's coming up. Cheers.